And I would like to invite Dr. Arad Rushev from the University of Ottawa, who will speak for the present students and postdocs of Professor Boyd.
Okay. Hi, my name is Orad Rushev. I'm sorry I'm not Marlon Scully. I'm not, no. I'm one of Bob's current postdocs. Unlike most of the people in this room, Bob still has plenty of influence on my future and my career prospects. But I'm going to throw that to the wind because we're all having a lot of fun telling great stories about Bob. So before I talk about some of the work I've done with Bob and that we've published together, I thought I would tell you a little bit about what I know about Bob. So this is one of the first few times that I met Bob. This is with my old advisor at Harvard. This is Bob with the beard. And this is kind of as far back as my history with Bob goes. However, I have some key insight into younger Bob. So before 70-year-old Bob, there must have been a 10-year-old Bob. This is Bob playing with this app on my phone, trying to see what he'd look like if he was younger. And what I find amazing about this is actually, in fact, there's some really keen resemblance between what he actually did look like when he was younger. There's been a lot of talk about Bob's sense of fashion. So Bob loves headgear in particular, and over time he has very quickly been able to convince me to partake. This hat is a Pakistani hat known as a pakul, handed to us as a gift from a visiting student here. Rashid, if you're here, raise your hand. He's gone, all right. There's, of course, this is when I invited Bob over for dinner. He happened to be in Montreal, and so we had dinner with my parents. And of course, my father enthralled him with stories throughout the night. This is actually more a dig at my father than it is at Bob, so I'll be sure to tell him this got a good laugh. Yes. Anyhow, so now let's talk a little bit about research, and then maybe there'll be a bit of like a touching moment at the end. So nonlinear optics are important. This is like the one room I don't need to describe why nonlinear optics are important to. I will point out, though, that I absolutely love this figure. This is of an octave spanning frequency comb, and I believe it's from Alex's group. This is one of my favorite figures to describe why we like nonlinear optics. This is really such a beautiful result. And one thing we'll point out, that I'm going to point out, is that we really want strong nonlinearities because that allows us to have smaller devices and lower operating thresholds for all sorts of applications. And for those of you that aren't familiar with this work that I'm about to describe, I'll give you a bit of a brief history. So the standard material by which we measure nonlinearities is silica glass. It is a very linear material, which is why it's used for, I guess, long-haul communications. This is another series of different materials, and usually when you talk about the nonlinearities, it's easy to describe them in terms of how much more nonlinear than glass they are. So for example, you have silicon nitride, which is about 10 times as nonlinear as silica. There's silicon, which is about 100 times, and then there's chalcogenide glass, which is about 600 times as nonlinear as silica. Now, recently, this is the work that Bob and Zahir and others here in Ottawa did that attracted me to Ottawa. A new class of materials known as epsilon near zero, or ENZ materials, have been discovered, and they have these incredible nonlinear properties. And I'm a bit surprised that no one has really mentioned it up until today, given especially that Nader's in the audience. And in short, there are two materials that have been used to demonstrate these really nice nonlinearities. Excuse the formatting, but basically there's ITO, which we work on here in Ottawa, which has a really large nonlinear coefficient, which is 600 times that of chalcogenide glass is. So not even 600 times that of silica, but 600 times that of chalcogenide. And there's aluminum doped zinc oxide, which also has a nonlinearity larger than chalcogenide, but in particular, it's delta n over n, so its change in refractive index over index is over 4. Which means that you actually have larger contributions to nonlinearity, to the refractive index from nonlinearity than the linear refractive index itself. And so these record large nonlinearities have raised some questions. This is some statements that I found in the papers. Let me read them out to you quickly. The usual perturbation expansion description of nonlinear optics effects is not applicable for this material at high intensities. Our results challenge the notion that the nonlinear optical response is only a perturbation to the linear response. This is from Bob's paper. And then from the enemy, the rivals, they say, this large modulation places the NZ nonlinearity in AZO in a regime where the approximation of expanding the material polarization in a power series breaks down. So when I first started working for Bob, we decided to address this question, which is, do we really need to change our fundamental understanding of nonlinear optics as a perturbation to linear optics? And so these are the three parts of my talk. The first is, where do these large nonlinearities in ENZ materials come from? Next, we'll present a more appropriate model for nonlinear refraction in ENZ materials. And finally, we'll quantitatively verify whether or not the power series expansion description of nonlinear optics remains relevant. And I'll give you a bit of a sneak peek. It does. Of course it does. Why would it not? So first, what is an epsilon zero material? So it's a material where the permittivity epsilon goes to 0. Now you might think that this is really exotic, right? Permittivity of air is 1, so how could there possibly be something less than 1? But it turns out it's pretty common. And so for example, we work with indium tin oxide here in Ottawa. Indium tin oxide is really actually indium oxide doped with a little bit of tin oxide. And it turns out that it has a plasma frequency, or what we call zero permittivity wavelength, in the IR at about 1200, 1240 nanometers. So here we have just a dispersion curve for ITO, and you can see it's got this really nice epsilon near 0 wavelength right over here at about 1240 nanometers. Permittivity vanishes, how nice. So Zahir took one of these samples, he goes into the lab, he measures the nonlinearity, and what does he find? Whoa, the nonlinearity really peaks over here at this exact same wavelength, 1240 nanometers. And in fact, if you plot chalcogenide glass, it doesn't even register on the scale. I mean, this is so much larger than anything anyone's ever seen before. It is really, really tremendously exciting. And this is what has been reported in Science back in 2016. And this is why I'm in Ottawa. So thank you, Bob, for this work. So first question is, where does this nonlinearity come from? Well, first let's go back to just the basics of nonlinear optics. If this is unfamiliar to you, there's a book I can recommend. But basically, there's what's called the intensity-dependent index of refraction. So you have a linear component, and then you have this nonlinear component that is proportional to the intensity. And if you go through some of the math, you can actually derive what this N2 value is in terms of the Chi3 susceptibility. Now, Bob likes to say, this is a material property, and this is the response of the material. So that's how we distinguish the difference between what we see in the lab and what the material actually does. And I'll point out quite nicely that you have these two factors of n naught in the denominator, which kind of hints to the fact that if you have a small value of n naught, you must have an infinite value of nonlinearity. But I mean, we all see this, and your first thought is like, a value of infinity just doesn't make sense. There are no infinities in nature. And so this was the problem we decided to tackle right away. And so we started with a nonlinear polarization to derive where this value of infinity came from. And you can very quickly get an expression for the refractive index from this. And then you take this and you usually Taylor expand it by assuming that the nonlinearity is much smaller than the index. Very, very reasonable assumption. And you end up with these expressions down here. And that's where you basically get the derivation for N2 from this set of equations. But the problem, I guess, is that this assumption depends, this derivation depends on an assumption that is just no longer valid. We actually are talking about a material where this goes to 0. So how could anything over 0 be less than 1? It's just not practical and not possible. And so the divergence of N2 is just a mathematical artifact. So what do we do? So we can go back to our derivation and we just don't do this Taylor expansion. We kind of stop here. And what we get is what we call the square root model. And if you like, you can write it in terms of N2 or in terms of Chi3. They're both equivalent, of course. And a few brief descriptions of the difference between the square root model and the regular linear model that we're all used to. So here I just have like a brief schematic comparing the two. And the first thing you'll notice is that you have this kind of weird saturation thing. But this saturation is entirely due to a Chi3 process. This is not the onset of higher order nonlinearities or anything like this. This is just the normal Kerr index, but what you would expect to see from a low index material. Second is that the linear model that we're used to is actually a special case for when the intensity is really low, right? Which also means that the consistency is maintained. So these two actually have the same. So that's really nice. So we have a model that agrees perfectly with what we had before, but doesn't have any faulty assumptions in it. So, of course, for all experimentalists, we want to compare this to an experiment. So what we do is we take a film of ITO in the lab, and we shine some very intense light on it, and we measure the transmission and reflection. And because the change in refractive index is so large, there actually is a substantial difference in what is transmitted and what's reflected. So that is, the Fresnel reflection changes, which is pretty remarkable. And this is what you get. See, the reflection starts at some value and then eventually goes down. The transmission starts at some value, eventually goes up, all as a function of intensity. It's pretty amazing. And you can use these to extract what the refractive index of the material must be. And if you just plot the linear model, you see there's of course some agreement at the beginning, but you very quickly start to deviate. If you plot the square root model, you get really nice agreement. So we're pretty happy with that. So now we can finally go back to address our original questions about reformulating the laws of nonlinear optics. So the question, does the approximation of expanding the material polarization as a power series break down? And can we still treat nonlinear optics as a perturbation to linear optics in low index media? So I guess the first thing to figure out is like, well, when does the square root thing break down? So if you go to even higher intensities, you see that actually even the square root model struggles to agree with the experimental value. And so we decide to add some nonlinear effects. And the question really is, how many of these are we going to need to add? Of these higher order effects we're going to need to add to be able to agree with the experiment again. Because if it's an infinite series, then the perturbation method no longer works. And it turns out that you get this really nice fit with just 2 more parameters. So actually, I don't see why the series should diverge. So nonlinear optics so far is safe. And then the last thing we got from this work is we can actually estimate the contributions of the different orders to refraction. And you can use those parameters we extracted and see how much each one contributes to refraction as a function of intensity. And what's really remarkable is you notice that the 5th order nonlinearity, the 3rd order nonlinearity, the 7th order nonlinearity all exceed the linear contribution to refraction. So actually, this material cannot be, the nonlinearities cannot be classified as perturbations, right? Typically a perturbation is you have some solution and then you have a little tweak to fix it. But here we have like a little tweak and then a whole bunch of other things to correct it. It's something completely different from what we're used to. So to conclude my talk, so the linear model for the intensity-dependent index of refraction, the first thing we learn about in nonlinear optics, it just does not work in ENZ materials or any low-index media. You can actually correct it very quickly by just not making an approximation that you really shouldn't, and by using what we call the square root model. We've included higher order effects, and we find that these contribute more to refraction than the linear terms at the highest intensities. And finally, there is just no proof that the power series expansion diverges, and so we do not need to reformulate nonlinear optics. So this is, of course, I'll thank all the wonderful people that we've worked with over the years. Zahir is in the audience, so is Jer. Enno is a former postdoc, used to work with us, as is Israel, who are he's now in Mexico. And I thank you all for your time. And Bob, thank you so much for including me in your family. I think since I still have everyone's attention, I'll just tell one quick story about when Bob hired me, and he says to me, so when he first hired me, and he says to me, you know, I always tell my students that I'm always here to help them. I'm here to serve my students, do whatever they want. And I said, wow, that's really great. And he goes, but I tell my postdocs they're here to serve me. And so, Bob, I hope I've served you properly. Thank you. Yeah.